What is the weak nuclear interaction? If you ask a physicist this question, you will most likely hear something like, well, it is that thing responsible for certain types of radioactive decay. And by the way, this is a perfectly correct explanation. However, it explains very little in essence and gives almost no real idea of what this weak interaction actually is. As you may have already guessed, in today's video, we are going to try to find our own answer to this question. We will try to understand why this interaction is called weak, and also what role it plays in our universe. The weak interaction is one of the four fundamental interactions, or as they are often called, the four fundamental forces of our universe, along with gravity, electromagnetism, and the strong nuclear interaction. And for 3 out of these 4 interactions, we actually have fairly simple answers to the question of what they are. For example, gravity is the attraction between massive objects. In particular, we encounter Earth's gravity literally every day in our lives. Electromagnetism is also quite straightforward. We see how a magnet attracts iron objects, or how statically charged clothing sticks to our body. In school, we are told that objects can have a property called electric charge, and that oppositely charged objects attract, while like-charged ones repel each other. The strong nuclear interaction is also intuitive. It is the force of attraction between particles made of quarks. For example, it is what holds positively charged protons together inside atomic nuclei, opposing the electric repulsion between them. That is, 3 out of the 4 classical interactions are literally forces in the classical Newtonian sense of the word: attraction and repulsion. But what about the weak interaction? A classical example of the weak interaction is the beta decay of a neutron, which transforms into a proton while releasing an electron and an electron antineutrino. You will almost certainly hear this example in any explanation of what the weak nuclear interaction is. And this, once again, is a perfectly valid example. However, from the classical Newtonian point of view, it explains nothing and only adds confusion. Well, first of all, where exactly is the force here? Nothing is being attracted to anything. Nothing is being repelled from anything. One particle simply turns into several other particles. Secondly, at the initial moment, we have only one particle, the neutron. So when we say that as a result of the weak interaction it transformed into something else, a natural question arises. What exactly did it interact with? To understand why physicists classify the weak interaction alongside the other fundamental forces, we must take a step away from Newtonian patterns, although not yet outside the bounds of classical physics. We will certainly have to leave that comfort zone later, but for now, we will remain on familiar ground. In principle, interactions, including the 3 interactions that we could rather easily define above, can and should be understood not in the language of forces, but in the language of energy. Indeed, an apple falls to earth because gravity exerts a force on it, but also because the apple seeks to occupy a position where its potential energy, in this case, gravitational potential energy, is minimized. The same goes for electromagnetism. Oppositely charged objects attract in order to form a neutral object that no longer generates an electric field around it. In other words, interaction is not only and not primarily about force. It is primarily a mechanism by which certain physical systems transition into a state of lower total energy, including rest energy, that is, mass. And if we define interaction this way, it becomes clear why physicists list the weak nuclear interaction alongside the others. Indeed, let us consider the beta decay of a neutron. The mass of a neutron is 1.6749 multiplied by 10 to the power of negative 27 kilograms. As a result of beta decay, it transforms into a proton with a mass of 1.6726 multiplied by 10 to the power of negative 27 kilograms. In addition, an electron is produced with a mass of 9 multiplied by 10 to the power of negative 31 kilograms, and a neutrino is emitted whose mass is unknown but is definitely less than 10 to the power of negative 37 kilograms. This means that the total mass of the system after the reaction is lower than the total mass before the reaction. The very process of energy optimization of a bound system we mentioned earlier has taken place. It is somewhat like if our apple, instead of falling to the ground, turned into a helium balloon capable of floating above it. Also a way to lower potential energy, but not by means of force, rather by changing the nature and configuration of the objects themselves. In the macroscopic world, of course, we do not typically encounter this, but in the subatomic world, it is a perfectly ordinary phenomenon. By the way, sometimes the weak interaction does have a more familiar force-like behavior. For example, a neutrino can collide with a proton and cause it to change direction. That too is a form of the weak interaction, the so-called interaction via neutral currents. What this means, we will explain a bit later. So, if we agree that an interaction is any mechanism that reduces the potential energy of a system, then we can understand why physicists speak of radioactive decays as a manifestation of interaction. However, we are still left with the question, what is interacting with what? And here, we can no longer remain within the framework of classical physics. The answer to this question can be provided only by quantum field theory. You have surely heard of the concept of wave-particle duality, in which quantum mechanical objects sometimes behave like waves and sometimes like particles. Right now, we are interested in the part where they behave like waves. This is exactly the interpretation used in quantum field theory. And if we say that a particle behaves like a wave, then the question immediately arises, a wave of what? The answer in quantum physics is simple. It is a wave of probability. More precisely, a probability density of detecting the particle at a given point in space. We discussed this in more detail in our video about wave-particle duality. In this sense, it can be said that particles do not exist as such. There are only excitations in probability fields. In this view, a photon is an excitation of the electromagnetic field. An electron and its heavier siblings, the muon and the tau lepton, are excitations of the lepton field. As for protons and neutrons, they are different types of excitations of what is called the hadronic field. The presence of an electron, proton, neutron, photon, or any other particle in a given region of space is a consequence of the fact that the corresponding material field is excited in that region. If the field is not excited, then we do not observe any particle. But the field itself, of course, does not disappear. It simply remains in its unexcited or ground state. And now, if we look at the weak interaction, and specifically the decay of a neutron, from this perspective, it becomes clearer what is interacting with what. For example, before the decay, we have an excitation of the hadronic field, which we call a neutron. During the decay, part of the energy of this excitation is transferred to the electronic and neutrino fields, creating excitations in them, which we interpret as the electron and the neutrino. Meanwhile, the energy of the hadronic excitation decreases, along with the total energy of excitation across all three fields. If we say that interactions happen not between particles, but between the corresponding material fields, then the question of what is interacting with what simply disappears. We just need to stop describing such processes in classical terms, and instead speak the language of quantum physics, the only language in which these processes can actually be described. That said, we should also remember that quantum fields themselves are not exactly real objects either. They are just a way of describing the state of a physical system, such as the vacuum. But we have discussed that in a separate video, and there is no need to repeat it here, especially since all these subtleties are not directly related to the topic of our discussion today. We can also approach the problem from another angle. In quantum physics, any interaction occurs through the exchange of one particle by another, and these exchange particles are known as carriers of interaction, or more formally, gauge bosons. For example, electrically charged particles interact by exchanging photons. The strong interaction works through the exchange of gluons, which mediate the interaction between quarks and quark-based particles. The weak interaction also has its own carrier particles, known as the W bosons and the Z bosons. The main difference between the weak interaction and the others lies in the fact that its carrier particles, unlike photons and gluons, have both mass and electric charge. If an interaction involves the exchange of a photon, which carries only kinetic energy and momentum, then the interacting particles can only change those same properties, their kinetic energy and momentum. But if the interaction involves the exchange of a massive carrier particle of the weak interaction, then the interacting particles may also change their charge and mass. And since charge and mass are what define what kind of particle we are dealing with, it logically follows that the type of particle changes during weak interactions. One particle becomes another. The beta decay of a neutron looks like this. A neutron emits a negatively charged W boson, thereby increasing its own charge by +1 in order to satisfy the law of conservation of electric charge. As a result, the neutron becomes a proton. Then the W- boson decays into an electron and an electron antineutrino. But the weak interaction has not only charged carrier particles like W bosons, but also neutral ones, the Z bosons. An exchange of Z bosons does not change the electric charge of the particles. They remain the same as they were. The exchange results only in a change in kinetic energy and momentum, which looks like attraction or repulsion. In other words, like a true force in the classical sense. This is the so-called interaction via neutral currents, which we mentioned earlier. And now, an attentive viewer might ask, if Z bosons have mass, then shouldn't exchanging them change the mass of the involved particles? And the answer is yes and no. The thing is, in particle physics, there is no special law of mass conservation here, as there is in classical chemistry. Instead, it is total energy that must be conserved, in all possible forms, including mass. By the way, even in chemistry, the law of mass conservation doesn't really hold strictly. The mass of substances after a chemical reaction is actually not exactly equal to their mass before the reaction. It's just that the difference is so small, chemists don't need to worry about it. However, in quantum physics, even tiny differences in mass do matter. For example, the tiny change in mass that occurs during nuclear transformations, such as beta decay, is the very source of energy in nuclear reactions, again according to that same Einstein formula. But the most fascinating part is this. Even the law of energy conservation in quantum physics is not followed in an absolute sense. The total energy of any quantum system undergoes what are called quantum fluctuations. That is, the energy can become slightly larger or slightly smaller, and the amplitude of these fluctuations increases the shorter the time scale on which we observe the system. These fluctuations can, and should, be interpreted as the appearance and disappearance of so-called virtual particles. We discussed this in a separate video. The link should be appearing on your screen now. When we talk about carrier particles, especially the carriers of the weak interaction, we are actually referring to virtual particles for which a temporary violation of energy conservation, and therefore of mass conservation, is not surprising at all. However, quantum fluctuations can only cause such violations on very short timescales. This means that virtual W bosons and Z bosons can exist only for a tiny fraction of time. Given their rather large mass by subatomic standards, approximately 1.5 multiplied by 10 to the power of -25 kilograms, their lifetime is only about 3 multiplied by 10 to the power of -25 seconds. These timescales are typical for the weak interaction. It either occurs within the lifetime of a virtual boson, or it does not occur at all. Accordingly, the range of distances over which weak interactions can happen is limited by the lifetime of the W and Z bosons multiplied by the speed of light, which gives us a distance of approximately 10 to the power of -18 meters. This is an extremely short time and distance even by subatomic standards. For example, in order for the neutrino-proton scattering mentioned earlier to occur, these particles must come within 10 to the power of -18 meters of each other. By comparison, the so-called effective charge radius of a proton is just under 10 to the power of -15 meters, which is about 1,000 times larger. In addition, the process of virtual W or Z boson creation is probabilistic, which means that even if the particles come close enough, the boson must also happen to appear in time and successfully transfer the interaction between them. In short, because the W and Z bosons have mass, and quite a large mass at that, the weak interaction does not occur very frequently. For example, the average lifetime of a free neutron before it undergoes beta decay is about 15 minutes, which is practically an eternity by atomic and subatomic standards. That is precisely why the weak interaction is called weak. Although, to be more accurate, it might have been better to call it rare. Even so, this weak and rare interaction plays an enormous role in our universe. It would not be an exaggeration to say that without the weak interaction, the universe, as we know it, simply would not exist. Indeed, earlier we mentioned that the weak interaction allows for the optimization of energy and mass in quantum mechanical systems by means of mutual transformations of their components. So far, we have considered this using the example of neutron beta decay. However, the opposite process is also possible, inverse beta decay, in which a proton transforms into a neutron. For free protons, this transformation does not happen, of course. It is energetically unfavorable. But inside atomic nuclei, where many protons and neutrons are present together, this transformation can become possible. A classic example is the helium-2 nucleus, also known as the diproton, a structure composed of two protons. There is electrostatic repulsion between the protons, while the strong nuclear force, which usually binds nucleons together, is weakened in this case because of the Pauli exclusion principle. The two protons must have opposite spin directions. As a result, this kind of nucleus is not very energy efficient, and its mass is about 3.345 multiplied by 10 to the power of negative 27 kilograms. For the same reason, this nucleus is unstable and can be destroyed by even minor external influences. However, if one of the protons in the nucleus undergoes inverse beta decay and turns into a neutron, then the Coulomb repulsion disappears, and the Pauli exclusion no longer applies. As a result, the nucleus becomes more stable, and its mass decreases to 3.345 multiplied by 10 to the power of negative 27 kilograms. What we get is a stable, heavy isotope of hydrogen, known as deuterium. In other words, without the weak nuclear interaction, which opens up additional channels for energy optimization in atomic nuclei, our universe most likely would not contain complex nuclei at all, and therefore would lack the full diversity of chemical elements that we observe and that make up everything, including you and me. And if we think even further, we realize that the very existence of protons, neutrons, electrons, and indeed all matter as we know it, is also something we owe to the weak nuclear interaction. I am referring to the unique ability of the weak interaction to see the difference between particles and antiparticles. From the perspective of all other fundamental interactions, particles and antiparticles are nearly identical. For example, we can assemble an antinucleus from antiprotons and antineutrons, and its properties will be basically the same as those of a nucleus made from ordinary protons and neutrons, with the only difference being that an atom with such a nucleus would contain positrons, that is, anti-electrons, instead of regular electrons. Roughly speaking, we could simply replace all particles in our universe with their corresponding antiparticles, and essentially there would be no difference between such an anti-universe and our own universe. Or rather, there would be no difference, if not for the weak interaction, which apparently behaves differently depending on whether a particle or an antiparticle is involved. One example of this asymmetric behavior is the phenomenon of meson oscillations, particularly in neutral B mesons. A neutral B meson consists of a B quark and a D antiquark. A neutral anti-B meson, in contrast, consists of a B antiquark and a D quark. During the oscillation process, the B quark emits a W plus boson and becomes a T quark. The D antiquark absorbs that W plus boson and becomes a U antiquark. Then the T quark emits a W minus boson, turning into a B antiquark, and the U antiquark absorbs the W minus boson and becomes a D quark. In this way, the neutral B meson transforms into a neutral anti-B meson. This same process can also occur in reverse, so the anti-B meson can transform back into a B meson. In nature, B mesons and anti-B mesons are constantly switching between each other, as if oscillating between the two states. This is what is known as meson oscillation. Now here's the interesting part. If the weak interaction did not distinguish between particles and antiparticles, then the probability of transition in both directions would be equal. That is, a B meson would become an anti-B meson just as easily as an anti-B meson would become a B meson. However, experiments show that the probabilities are not equal. The B meson is less likely to turn into an anti-B meson than the reverse. In other words, the B meson appears to be more stable than its evil twin. To put it more simply, within the weak interaction, the universe seems to prefer particles over antiparticles. The difference is small, only a fraction of a percent, but the very fact that it exists is remarkable. And it is entirely possible that this very difference, created by the weak interaction between matter and antimatter, played a key role in ensuring that any matter at all exists in our universe. Indeed, according to current scientific understanding, all particles that make up modern matter, such as quarks, the protons and neutrons built from them, as well as electrons, should, in the first moments after the Big Bang, have been created in pairs with their antiparticles. But such pair creation is a reversible process. Alongside it, there would also be annihilation, particles and antiparticles destroying each other, and as a result, there should have been no net accumulation of matter. In that case, our universe would have ended up with no stars, no planets, and no interstellar gas, filled instead only with photons, perhaps with some neutrinos. The fact that matter exists in our universe tells us that there must have been a symmetry violation between matter and antimatter, and it is the weak interaction that gives us insight into how this violation might have occurred. Unfortunately, calculations show that the weak interaction alone could not have produced matter in the quantities that we observe today. This suggests that there must be other mechanisms that also violate the symmetry between matter and antimatter. What these mechanisms are, scientists have yet to discover. Moreover, we still do not understand why the weak interaction distinguishes between matter and antimatter. The mechanism behind this is still unknown. We can only observe that it happens, but the reasons for it remain a mystery, one that still needs to be solved. Of course, it is impossible to explain and explore all the details and nuances related to the weak nuclear interaction in a single video. For example, we did not discuss how the study of the weak interaction led scientists to propose the idea of the so-called Higgs mechanism, which is how elementary particles acquire mass. We also did not address the unification of the weak nuclear interaction and electromagnetism into a single force called the electroweak interaction, the first real step toward what is known as the grand unification, in which a single law would describe all fundamental interactions at once. That said, there is a bright side. Each of these topics, as well as other subjects related to the weak interaction, can be explored in dedicated videos where we will no longer need to explain what the weak interaction is and how it works. And if you enjoy what we do here on the channel, I kindly ask you to support our work. You can become a sponsor right here on YouTube or on our pages at Patreon and Boosty. A link to the latter should now appear on your screen, and all necessary links will also be included in the video description. That's all from me for today. I wish you all the best, dear friends, and see you again in our upcoming videos.